Okay. Hello, everyone. Can you hear me? Yeah. Great. So today I'd like to talk about modules, and it has a different. This talk has a different name in the schedule, but since it was accepted, the modules were also accepted in the C++20 standard, so I kind of give it more clickbaity name. So modules are in C++20. And why am I talking about the modules? Because I work in JetBrains on C-Line, and modules and stuff like that is very important and very crucial for the intelligent IDE. So I was following all the progress on modules with great interest and great care. So a quick shout out to our sponsors. Without them, I wouldn't be standing here. And so the modules are accepted in C++20 recently. And it's one of the most anticipated features in C++20 and in C++ maybe ever. And I've never heard anyone saying, oh, well, I'd really want concepts in C++20 back 10 years ago. But for modules, everyone was talking about modules and how they want them, like for several, like maybe for 20 years already. But it's also a most misunderstood feature because everyone wants everything from modules and to solve every problem with modules. And in this talk, I'll try to show what problems can be solved and what not. And it also, at the same time, most revolutionary feature because it changes the way what C++ code are and how we're looking at what's written and how we understand it. But at the same time, it doesn't introduce almost no new syntactic or semantical constructs in the language. So your domain-specific code stays the same, but it gets interpreted differently by the compiler. So why should we care? Why do we care about modules and what problems they intended to solve? To answer this, let's discuss briefly the current compilation model, how C++ code is compiled. It's inherited from C, and it's based on a preprocessor. And this means first, then the preprocessor inform on textual inclusions are used for code reuse. And that's the only way of code reuse in C++. And the preprocessor doesn't know about the rest of the language semantics. So for example, you can have like your semicolon in your header file, and just instead of typing semicolon, you type include semicolon.h, and it would work. So preprocessor doesn't care. It works on tokens and just pure tokens. And it has some complications. First, it's speed, obviously, and it's speed and build performance. Because this hello world, when expanded on my machine, it takes about 30,000 lines on my machine after preprocessing, and the compiler can't cheat. It should parse each and every declaration in these 30,000 lines, and it should do it for every file in your project, expand and parse. And for big companies and big projects, header files with 1 million lines of code after preprocessing is something not unheard of. And that's because the amount of code you have to compile for your project grows super linearly. When your project grows, first the number of translation units grows, so the number of your CPP files, and also they grow themselves in size. Also, the number of connections between translation units and between headers also grows. So in practice, build times doesn't scale when the project size grows. So that's one thing. But that's not all. Another thing is leaking names. So have you ever seen any standard library implementation in the world? Like if you open your vector header, it looks something like that, and it's very ugly. And why is that? Because some user, might have this innocent-looking header that defines some allocator and some class, and just can include it before the vector. And since preprocess doesn't care about semantics, it doesn't know what vector is, what your class is, it just pastes everything together, compiles it, and you have name conflicts. And all the names, all the user names from previously included headers could be in your current scope. And that's especially bad for library writers because, like, when you're writing application code, you can just do something else. But when you're writing a library, a header for a library, it has to work anywhere. basically. And while standard library implementers have the luxury to use reserved identifiers like with double underscores or started with an underscore, the rest of the library authors doesn't have this luxury. And it's kind of painful. And it's also unsafe because your code can change meaning depending on where it's included. Another thing is one definition rule violation. Basically, to put things simply, one definition rule is that you may have only one definition in translation unit for like an entity, a function on a class. It's easy. But what's not easy is that if you have multiple definitions of the same entity in your program, in the compiled together program, they all should be the same. Basically, they all should be the same token stream. And why is it so? Because, well, since translation units are independent and they compiled independently, and compiler doesn't know about any dependencies across them, it's naturally your classes and functions are repeating itself in these translation units. So if they are for some reason different, the program is ill-formed and no diagnostic required. Basically, it's not required because it's very hard to do. And your program might be broken and you will never know it. And it also can happen very easily, and it does happen in real life. For example, if you have two translation units in two libraries, one is compiled in debug mode, one is compiled in release mode, and then you link everything together, the classes and functions written there can be very different, but in general, compiler has no way to tell that. And it's very easy to do accidentally, or via like transitive includes on different stuff, and this a major source of pain points in the big projects. Another issue is accidental dependencies. Like imagine you're writing this, you've written this lib1, and then you are writing this lib2, and you're accidentally using a class from lib1. You never intended to do so, you just, well, copy-pasted it from somewhere. And if you're unlucky and all your headers are always in this order of inclusion, directly or indirectly, you will never know about that until you, well, discover it at some point. And it could be very difficult to untangle if you discover it late in the development cycle. So it can be just invalid library pulled in or just broken layering inside a big project and stuff like that. So modules are intended to improve all of these situations. They never can solve any of this fully. So the builds wouldn't be instant. You still have some name collision, stuff like that, but they intend to help with this greatly. And let's start with like the basic modular hello world thing. It's just, it's not very different from header-based hello world. The only thing is that instead of this includes IOStream, you do this import standard.io directive. And what does it happen? It means that somewhere in your file system, a module called std.io exists. And it's parsed separately, and it's when it's parsed, it's stored in a separate file. Usually it's a compiler-specific format, and when the compiler reaches this import declaration, it, instead of pasting the text of the IOStream here, it just loads the thing it parsed before and uses it. And it's way more effective. And another important thing, like it's not has to be what I've just stated. Implementers can employ different implementation strategies because it's implementation defined, but it's one of the existing and plausible strategies to implement. Parse beforehand, store on disk in some file, and just load some internal compact representation of what you parsed. So some extra trivia about this small hello world. The code is the same. It says stat.io, but these dots mean nothing. So the name is just a sequence of characters and dots, and dots has no defined meaning, is not related to file system and stuff, and nothing like that. Also, modules are orthogonal, completely orthogonal to namespaces. As you can see here, you still have to type stat : cout and so on. because it's not like if you import a module, you get access to symbols in its namespace or nothing like that. It's completely orthogonal, and the names match by coincidence because someone decided it was a good idea. It's nothing in the language that specifies any kind of match. Import declaration go on top of the file, so you can have a list of imports there. We will get to that later, why it's important. And another thing to consider, like imagine if you have an error in your main in this file, in your main function, and you have to compiler has to show you a function, an error message. And because it's all templates, it has to show you instantiations and template instantiation backtrace and what function was instantiated and stuff like that. And this means that, and all compiler has is this module that is it imported. So this means that the data stored in module is very similar to the data stored in the actual source file. Usually it's just an AST representation in some form. So also this means that it's not some kind of intermediate representation, not some kind of assembly-like stuff, not some kind of object compiled thing. It's very close to source, and basically it can do everything the source can do, and it can't do anything source can do. So you can see it's not really a way to hide code from the user. User will have to see it eventually. Another example. It's a simple library. It's just header-based. It's just a library which has two functions in its interface. One is function and one is function template. And also it has this helper function that has to go in the header file because, well, you can put in CPP file, obviously. So because it's not a part of interface, we in header world, we need to protect user from using it accidentally. So we put it into the detail namespace. And how would a modular version of this function look like? So we now seen the first module translation unit. So modules are essentially a way to get names from other translation units. So what I have here is a so-called module interface unit. It's translation unit, but for a module, and more specifically for a module interface. And what indicates that is that export module keyword that starts this translation unit. So it's module called simple lib, and it's interface unit of that. And here we have three declarations. And you can see that two of them are exported. They are prefixed with the export keyword. The last one is kind of obvious, except we now can more easily put implementation into the same file. And the non-exported function base is interesting because it doesn't have an export keyword next to it. So this means that it's so-called, this means that the function is only available inside this module, and users can see it. I will show some examples later. So if you import this module simple lib, you can't access base. You can access only two functions. So the details namespace is redundant now, and I've just omitted that because it's no use here. Also you can see its template functions also can be exported, obviously, and it's kind of a better solution for the export template that we had in C++98 that were never implemented basically by mainstream compilers. But the issue with that is that everything is one file, and what if it's very big and it's not always convenient. So you can have your one module and split it into several files. For example, here I still have my module interface unit, but I don't have the function full definition there. So I have another translation unit. It's called module implementation unit. You see it starts with keyword module but without export. So I put the implementation there. And basically it doesn't need additional imports. Module implementation units can see symbols from module interface units. And well, it's basically kind of straightforward. Also, I forgot to mention that this module keyword and this import keyword, these are context-sensitive keywords, and if you have your variable or your field of your struct called module, it would still work, continue to work in C++20. It was a heated debate because first it was just hard keywords, but some companies said just it over our dead bodies, and we can't afford that. So now it's some sophisticated heuristics how to detect that this module is a keyword and the other module is just a variable name or type name or something. So more about exporting and importing, some more examples. Two features here. One feature is if you have a namespace n in module 1, you can mark it as export, so all its contents, all declarations containing in it would be implicitly exported as well, and can be used by the clients. Another feature is in module 2, it's called export-import. So this funny way to say I'm importing this module for myself, and I'm at the same time exporting all its export symbols to my clients. Because otherwise, if we don't have this feature, the clients of module 2 would have to import module 1 by themselves if they wanted to use stuff from there. So, and another funny thing is how non-exported types behave. So here we have struct s, which is not exported, but we have a bunch of functions returning it. So in main.cpp, it's normal translation unit. It's not non-modular, but it imports a module. We can use a function from module 2, obviously. We can use a function from module 1, from a namespace, because of this export-import stuff. And we can create a variable with type s, but without specifying the type, using auto variables. We can access its members and so on, but we can't spell out the name of the type s. It's kind of similar to how function local types work. You can have an a function that returns a struct defined inside the function. It's kind of same stuff. So you can use decal type on s and still have access to s. Yeah, that's some features that modules have. And I've mentioned very basic features. Let's discuss now how it's compiled. So that's our current world. That's how we live now. We have several translation units. They include some headers. Many of them include the same headers several times. So they got compiled by the compiler, produced an object file, and object file got linked into like a library or something. Note that, see that there is no build steps or specific build artifacts for headers. Headers are just included as a part of the CPP file compilation. Everyone knows that. With modules, it's kind of more complicated. It's kind of the similar setup, but instead of headers, we have modules. So these CPPM files are module sources, and CPP are translation unit sources. And as you can see, each module source has now two artifacts. First, it has it may have an object file as before. If there is some function written in this module, it has to be put somewhere for the linker. It can has an object file, but also it has this BMI, which people call this artifact differently. I call it binary module interface. This is the thing I was explaining that compiler-specific data that it writes after it parses the module. So, as you can see, modules can depend on other modules, and they depend on these BMIs during the compilation. So, when you build first module, get a BMI from it, build second module, use a BMI from the first module, get a BMI for the second module, and so on. And then you build your translation unit. It depends on some BMIs, and then you link everything together, like like it was before. So see, it's less straightforward. It has more steps. It has more dependencies. But now modules are first-class citizens here, not unlike headers. And build system is aware and should be aware of the modules. And another thing, just to mention, it's the probably most common misconception about modules, that these BMIs are not distribution artifacts. In general, you don't want to distribute them. You want to distribute source code with, as it was with headers. Why? Because BMI is heavily dependent on the compiler, on the tool chain, on the flags used to build it. And there is some work on providing portable BMIs, but it's on early stages, and honestly, I don't see compiler vendors agree on that. So BMIs are tied pretty heavily to everything, to your environment, to your type sizes, to your defines passed to the compiler, to front-end flags, and stuff like that. So, and in only very few circumstances you can distribute BMIs together or maybe instead of your source code. First, if you work in a large company and you know everyone has the same setup, to save time, like you can have this kind of distributed compilation, and to save time for everyone, you can distribute BMIs with you, for example, header-only libraries, or I should say probably module-only libraries now. But that's when you know everything is on the same page, everything is using the same flags and same compilers and stuff like that. And the similar situation is with a couple of vendors that ship toolchain, compiler, standard library, debugger, IDE, all in one bundle together. That's Microsoft and that's Apple. And they could get away with shipping BMIs for standard library with it, also to save some time for the people. But it's still essential to ship code with it, to ship source code with it, because if you want to configure your compilation with some non-trivial preprocessor flags, like, I don't know, enable assertions and stuff like that, your BMI would become invalid. You have to pass, build it again with a new set of flags. So yeah, and also this means that module is not about package distribution. So people always sometimes hope that with modules we can more easily download our favorite XML library or remove some stuff for a standard library, put into packages. It's not about modules completely. We're on exactly the same page as we are with headers. Modules don't help with that. We have to do packaging and not modules for that. Yeah, and also about compilation and linking stuff. So as you saw, there are some just normal function modules that have to go somewhere in some object files and linked in some binaries. And what we have now for functions in C++ is three types, for symbols, is three types of linkages. We have external linkage. It's when a symbol is global for the whole link program. It's internal linkage with the symbols local for the translation unit, and no linkage is type alias and other stuff. So what about exported and non-exported symbols? For exported, it's kind of easy. It's the old external linkage stuff. If you see an exported function, it's a function with external linkage. So you still can't link two modules with two same named exported functions together. And note, it's unrelated to module names. It's just as before with headers. But for non-exported function, that's more interesting because you can't make it external linkage. So if you do that, then the module internals will affect each other basically. And you can do it internal linkage because module consists of several translation units. We saw it too, the interface and implementation. And it should be seen across these translation units. So what do we do? And for that, the new type of linkage was introduced. It's called module linkage. And it's kind of in the middle. And basically what it states is this function is visible inside the module, all the translation units that from this module, but not from outside. And technically, it's probably implemented by mangling the module name or module identity some way into the function mangled name, as it is with namespaces and with like anonymous namespaces, similar to it. So this is about linkage, and another important thing that was heavily debated, and there were several options about how to use preprocessor. Because in ideal world, we get rid of the preprocessor with modules and just use like modules for code reuse and context for like constants. But it doesn't happen. For now, there is a lot of code with defines with macros, and a lot of things can be done yet with just plain C++ without macros. So we have to deal with macros some way. There was idea about that, like just don't do anything and let the preprocessor do its own thing separately, or introduce and use new special preprocessor directives for exporting macro names. But the final result is kind of simple, I'd say it's kind of hacky, but it's simple. So two things. First, when you external macro names don't affect the internals of imported module. It's obviously because it could be compiled separately, and before we're compiling like this main CPP file in this example. But second, after the import, all macro names from the module started to become visible in the translation unit it's imported in. So in this example, we have two modules. One just defines a macro, and the second one defines b macro if a macro is defined. Imagine if it were headers, so we'd have a macro and b macro both defined in our main CPP file. But with modules, we have a macro defined right after a import a declaration is finished, and b macro is not defined because a doesn't leak inside b. So it's kind of this workaround for how to deal with macro names coming from modules. Okay. So, and also about transition paths and how to deal with existing code. If you want to start using modules, you will have some trouble probably. Because full rewrite is often unrealistic, and naive approaches doesn't work. So if you have a module and you want to use some parts of your non-modular code, what you're going to do? You're going to include your file into your module, but it doesn't work. Because first, it might be slow, because for each and every module, it would repeat all the declarations from all the headers and store it into these BMIs. But what's worse, it just doesn't work, because these symbols from the headers became non-exported, and that's probably not what you need. So the modules that merged into the CppCon19 offer two features for the transition of your existing code. First is basically came from client modules, more or less, from the old existing implementation, and it's called now header units. So in your project, probably most of your headers are kind of good. They are self-contained, they don't depend on external names, they behave exactly the same every time it's included and stuff like that. So you could say, outside of your source, somewhere in your build system or somewhere in your configuration, that this header is good header. Turn it into a header unit. And this means two things. First thing, you can import it as a module. And what this means is this header would act as a module. And all declaration from this header would implicitly become exported. So you mark your header as good, and then you can import good.h, and it would be a module called, it would be a header unit, not a header. But the funny thing is the other thing. You can, in your old non-modular code, when you have, like, you include any declaration all mixed up, you can have this include good.h directive. And upon seeing this, compiler will avoid using preprocessor to include this good.h, and it would just treat it as it was an import declaration here and just load a module. Yeah, and as you probably might guess, a lot of things could go wrong if your good.h was not so good and dependent on some macros. Your source code behavior might silently change. Or if you have some static variables there, your behavior would silently change. So it's up to you to pick a good headers to make turn into header units. Another feature, and it's very different from the first one, that's from the original modules proposals brought to us by Microsoft, is global module fragment. So imagine you're starting to write a model. And as I said, you can't just include all your stuff there because it would be a part of your model. It's not what you want. So instead, you have this section before your model that's called global module fragment, where you can freely include everything you want. You can include all misbehaved headers, windows.h, stuff like that. And there are some funny things happening here. For all your models that you compile, all declarations from all these global module fragments are merged into a single kind of global module. And then it's got reused again and again during the compilation. But it would be very big if it done just in naive way. So it would leave here only used declaration and discard everything else. So if you include Windows H and then use one function from it, so this global module fragment, that's kind of another separate module, would contain only this one function. So to summarize, it's kind of header units. It's graduate modularization existing code base here and there. So this good, this good, this good. So yeah. And global module fragment is when you start to write new code, but you want somehow to use old header-based code, which you can't or don't want to fix. And now the interesting questions. How fast are modules? Fast, I mean the build speed. So many people want modules just for the build time improvements. And it's obvious that asymptotically the amount of work for the compiler is reduced, but build parallelism is also reduced greatly. Because you might need to pre-scan modules before builds, more of that later, it's not parallel. And with C++ currently we have like an unlimited capability of build parallelism. You can take each translation unit, and if there are no like dependencies between different targets, you can build it each separately. But for modules, it's a dependency graph of dependencies. You can, for example, probably you should build standard library first and can build anything that uses standard library before that. So it adds additional parallelism issues. And also, if you have like distributed or cached builds, transferring these BMIs, which are probably fatter than source files, are not exactly free. So for the clean builds on real-world projects, on like normal hardware people usually have, it's not like not a Intel Celeron and not 2000 core like supercomputer. And for the like normal projects people usually use, what build time improvements should we expect? I've done some experiments. I've researched some pre-existing implementations. I've read some discussions. I would say the range is about like that. So if you convert a project into modules somehow, if it's not very big, if it's not very small, you should see like about 50 to 300% build time reduction. Like it's complete speculation. It might be not the case, but I think it's an educated guess. And so if your project contains of small, simple headers with a lot of code in the translation units using CPP files, and all the declarations of headers are actually used in your module, used in your translation units. And or if you do a heavy template-based metaprogramming, when your headers just do nothing and you do all your work in your instantiations in your CPP files. Or if you have like 1 billion lines of header-only libraries all included in a single translation unit, module modules probably won't be very beneficial to you for the build speed. But if you have big headers and a lot of inline code there, or if you have headers like a giant header and only one or two declarations are used from there, or if you use context-based metaprogramming, which is going to be used more and more in the next years. So that's probably a good thing for modules. And anecdotically, I was told that when someone was inventing the context per functions, the modules were invented like a side effect of it, because you need a way to put your context per functions, not if there is a lot of them. So, but there are another cool things about the build time. First, using modules allows to incremental compilation even for better incremental compilation, because, for example, if you change a header and it happens to be included early in the translation unit, it just invalidates everything in the translation unit. And now, if you change something, but the rest of the imported modules might not be affected by that. And also, it could be used for building a single translation unit in parallel, because if it imports a bunch of modules, they can be built in parallel before the actual translation unit. So edited compile cycle might be faster when it will be implemented in the compilers and build systems. So what about the tooling? Because the story was like that. For C++20, everyone, after some discussions, every compiler vendor agrees on what's going to the modules, and everyone's reaching to the consensus. And then people who write build tools and other tooling around C++, they suddenly realize they have to implement all of that. And they started to raise the concerns. Because it's very complicated for build system compared to headers. Because build system has to know beforehand where to look for modules and in what order to compile them. And there are several complications for it. Because, for example, module name, it's implementation defined, but unlike header, it's actually spelled in the file. And you actually technically can go and change that to something else. So you can't figure out a module name without looking for the without looking inside the source file. So there are some solutions for that. You can depend explicitly on file names. You can pass mappings to the compiler for what file, what modules contains. And basically, that solution are currently discussed by SG15 group in standard committee. It's a tooling group, and it's finally found its purpose to discuss stuff around how to build modules, let's say. Also, this fun example, for example, you have two modules to the left, one imports another, and a user just changes these two files in this way. And after the change, the B module imports the A module. And what would you do with it? And before you launch, so when you launch the build system should know that, because it should build the modules in the correct order. So the solutions are manual specify dependencies. So in your build script, you have to write A module depends on B or vice versa. But it might be complicated because often modules are they're about as granular as headers, maybe a bit more, but it's not as granular as libraries. Like one module is probably one or several headers, likely, if you don't use headers anywhere else. Another option is to pre-scan sources. So you just open your files and see what imports what. But this also depends on the preprocessor, because as you can have an import declaration inside an ifdef, or you can build the binary model interface on the fly. So you don't build it beforehand. You reach the import directive, and you see somehow if there is no binary model interface for the module you're going to import, you build it again. That's how old Clang modules work, but it might be complicated some scenarios, and it also reduce build speed because you might do some extra work. And for this reason, because like a pre-scanning is one of the valid options, all the import declarations should go to the top of the file. But they're still affected by the preprocessor. You can have them inside an if-def block. And also, it's not applicable to header units at all, because header units in form of include good header may happen anywhere in the source file. You have to preprocess everything. But that's for build tools. But for other tools, in my opinion, it's kind of controversial. Not all people agree with it, but in my opinion, headers cause troubles and models solve them. Because now we get some meanings for the code that were previously in the headers. Because if a code is in the header, how would you analyze it? In what context? What if it is included twice in different places? What if it is included in different authorization units with different preprocessor macros passed to it? So now it's all doesn't matter anymore. Each module has its own meaning inside the build system. And we can see that this module belongs to this library, so we might skip analyzing this when analyzing that and stuff like that. And a lot of existing IDEs are already trying to do these kind of optimizations to not parse the header each time and just skip it and preload it from somewhere else, but it's all incorrect and heuristic based with headers because it can be done properly in general case. But with modules, it's kind of done automatically for you. So with the current implementation, it's not there yet for every major implementation. In Clang, there is active development and an experimental support available under this flag modules TS. Note that flag F modules is not about C++20 modules. It's about the Clang modules that were like long time ago. It's a bit different technology. It has like the same. It's based on the same technological foundation, but it has different semantics. In Visual C++, for several versions, especially minor versions, I think it's shipped to the users and you can use it under an experimental flag. And GCC is currently lagging a bit behind, so it's not yet merged into mainstream. It's developed in a branch. Well, hopefully, like during this year or so, it will be merged. And another kind of bummer is while modules are accepted for C++20, modularized STL is not standardized. So you, technically speaking, you can't use standard library with your modules. But some implementers have already some solution for that, so it likely would be standardized for C++23. And you should use just implementation, vendor-specific implementation in the meantime. And for the build system support, build2 build system and Boris, who is behind that, is pioneered some effort in the build system and like made everyone aware of the problems. And in CMake, there is a work in progress of the support modules, and also there is a patch in Ninja to enable that. And people say that it's complicated to write proper build scripts in Make with Make files to build modules, unless you explicitly specify the dependency between each separate module. So, the summary: modules are accepted, and it leads to more clean, more nice code, and less name leakage. Build times would improve, but not like in the order of magnitude, probably, for most of the projects. And implementation and tooling are not there yet, but they're quickly catching up. So likely, in a year or so, we can use modules in production code with the transition to them with the transition patches that's offered by the modules in C++20. Thank you. Any question? Any questions? Any questions? No questions. Oh, there is a question. There is a question here. I think someone What to do with the mic?
Thank you. I was wondering how it is possible to imagine you want to create a library that is capable of using the C++20, but is want to be retrocompatible with the old project that does not support C++20. How can you declare something that can be used as a module or can be imported as a header, normal header?
Yeah. So you either use this header units thingy. So you have your headers. You have your good headers that are marked as a module somewhere. So they can be just included in the old code base, but they can be also used as a header units and turned into a modules implicitly. That's another way to do it. One way to do it. And another way, probably, I'm just speculating, I've never done that, but is to start writing modules, like thin wrappers for modules, and use this global module fragment, include all your old headers, and do some, like...
Yeah, but in this way, you always need to create header files and then create a superset of modules over that header files, because otherwise all the not C++20 project cannot use that. So it
in this way, but not here. Here you can use just normal header files and mark them as header units.
Thank you.
Okay, now imagine that you have a medium-sized project with 100 of files. Now it's written with 100 of header files and then 100 of C++ files. If I'm going to modularize this kind of source base, do you imagine that we will have 100 of little modules or just a few large modules that make a few more C++ files together?
Well, it depends. It depends on what's written in these files. It can be 100 modules if like the files are highly disconnected, but it can be some fewer modules because I have not mentioned it here due to lack of time, but you can actually span a modules through a model implementation for multiple files. So you have several implementations for the same module. So you can have one bigger module, but most likely a module would not be the size of a library. It will be smaller than a library.
Thank you.
Okay, they say that time is over, I think. Thank you very much.